There was confusion at yesterday's. Oh, sorry. There was confusion at yesterday's dinner. MBA is my initials. That has nothing to do with Masters in Business Administration. So today we'll be talking about exploiting parallelism using not libraries or frameworks, but rather parallel primitives. And specifically in the context of SPM.Python, which is, how many of you know Python, the language? Okay. Heard of it? Okay. It's a high-level, very popular language in scientific computing. And what we have here is a self-contained parallel environment that allows people to explore or implement, with the basic infrastructure, 10 different forms of parallelism. The guts of it is patented, but today's focus is going to be on two new sets of primitives we are bringing online. The first one has to do with providing fault tolerance for OpenMPI applications. And it's kind of an interesting way of solving the problem. And the second one has to do with processing of massive graphs and data, again using Python the language, right? But before I get into the guts of it, a couple of interesting things. This is December 2011, and there's no consensus on what I mean or anybody means when they say exploiting parallelism. Ask 5 experts, what do they mean by exploiting parallelism? You will end up with 40, 50 different answers. It's astonishing. So what I mean when I use this term is that parallelism is nothing more than the management of a collection of serial tasks, right? It's as simple as that, as complicated as that. It transcends the moment. I have not qualified this statement. I didn't say that this is only true for x86 and not GPUs, or this is true today and not for Parascale. I don't think. I mean, this thing is going to hold true no matter what. At least that's my supposition. And management is a fairly loaded term. It includes things like scheduling of tasks, enabling and disabling of communication primitives, because it's not enough to talk about exploiting parallelism. We want to eliminate deadlocks from occurring in the first place. Now, the issue of deadlocks may not be a big deal for C++ programmers, but Python programmers, they don't like things when they get stuck. And we need a way by which to eliminate them. And of course, serial tasks come in two flavors, coarse grain and fine grain, right? This is the sum total. So the bottom line is this. When we talk about managing resources in the context of exploiting parallelism, it doesn't really matter what is being managed. The only thing that matters is how we manage it. So whether your serial task is doing something in IT or finance or life sciences, from the perspective of management, it doesn't really matter. That is important because that allows us as a provider of a capability to centralize these things, so less things for the developer to worry about, okay? And we convert these things into primitives. So that's the big picture. The other thing about the terminology is, this is one of the most famous, frequently asked questions on the web, right? Is exploiting parallelism easy or hard? This is one, and answering this question is the shortest way of guaranteeing that your traffic to your blog will go through the roof. I'm not as fascinated by this question. I mean, it is an important one. I'm much more fascinated by this question. What makes parallelism hard? What makes it easy? We know from experience that there are situations where it is easy. We know from experience that there are situations where it's hard. So the question is, to what can we attribute this degree of difficulty? That to me is more interesting. Because if we understand this, then the roadmap becomes much, much clearer. And my supposition is that it has all got to do with the gap between the developer's intent and the API of the parallel enabling technology. It is as simple as that. If the gap is large, that particular project is going to be frustrating, it's going to be deadly, it's going to be hellish. If the gap is small, it's going to be a piece of cake, it's going to be non-event. So for example, if I'm thinking in terms of MapReduce, and somebody is expecting me to use OpenMPI, which is a parallel enabling technology, right there, that's a red flag. Because I'm thinking in terms of MapReduce, and MPI is talking to me in terms of send receives. That gap has to be bridged, and it's the developer that has to do this. If on the other hand, I'm thinking in terms of MapReduce, and the primitive is talking to me in terms of MapReduce, well, that's pure nirvana. I should be able to write some code in 5 minutes, right? The gap is small. So this is the important thing here, that we want to close the gap between, we don't want to provide solutions that are close to the hardware. We want to provide solutions that are close to where the developer is. That's important. So then the next question is, if that is the case, then is there any way we can classify parallel enabling technologies? It seems like they're fairly important. And there are three kinds. PETs are nothing but means to an end, right? And there are three ways of going about thinking about this. The first kind of PETs are the bottom-up ones. The open MPIs of the world, the open MPs of the world, CUDAs of the world, they tend to be library-centric, and they tend to hug the hardware, not the developer. So the developer has to bridge this gap, and the code depicted here in green is the stuff that's authored by the developer. And that gap is so large that they have to navigate that. And there are no guiding principles that do this or do that kind of thing. So it's a very frustrating thing. But you get maximum flexibility and of course maximum headaches, right? The second kind of parallel enabling technologies take the opposite approach. They focus on a thin slice of the parallel landscape. And they come up with a top-down solution that is self-contained. And in that context, the developer is expected to provide specific, well-defined pieces of code. So for example, in case of MapReduce, the framework says, I want you, the developer, to provide me map, and I want you to provide me the reduce. I'll take care of everything else. The problem and so from a developer's perspective, these things are very easy to relate to, very easy to use. The disadvantage is that it's limited. I mean, notwithstanding all the buzz around Hadoop, at the end of the day, it is solving a thin slice of the parallel landscape. Okay? And then the third kind of parallel enabling technologies are self-contained runtime environments, of which SPM.Python is, to my best knowledge, it's the only one of its kind. And as I mentioned, the reason is we want to think of exploiting parallelism not in terms of libraries or frameworks, but in terms of parallel primitives. So for example, consider an analogy about this framework business. If I have 10 different forms of parallelism I want to exploit, and yes, it does matter which algorithms we use. It does matter which data structures we use. It's not like a one-size-fits-all is going to work. But we want to provide it in a way where the developer has an easier time to relate to. So anyway, we have 10 forms of parallelism we want to exploit, and we are limited to frameworks. What that means is we have to install 10 different installations, 10 different frameworks. They have their own lingo. Very frustrating. So it's like going from here to New York, and you want to drive. And you start off with a license that's issued by the state of California. You go on Highway 80. As soon as you enter Nevada, that's a different framework. The police are going to stop you. They're going to ask you for a different license. And by the way, in Nevada, we drive the other way around. I mean, that would be very frustrating. So the idea with self-contained environments is that you have only one environment you are installing. But because of these 10 primitives, you can exploit 10 different forms of primitives, of parallelism, right? So the result is something that's an acid test at the end of the day, which is what, on the left-hand side, we have things that we do all the time in the serial world. We are calling modules one after the other in a serial session. There may be I/O bounded, there may be CPU bounded, and we create a system flow. And we want to simply invoke these parallel versions of these modules in the parallel flow session. And here what I'm doing is I'm using the same 40 machines, for example, in 4 different ways within the same session. It's practically impossible when using frameworks. It's practically impossible when using libraries. And yet for the programmers of Python, they expect this kind of a thing, because they're doing that in the serial world and they want the parallel version to work this way, right? Okay, so as far as Python is concerned, again, we support multiple forms of parallelism, so we want to make sure that developers have a very easy time relating to this. So the idea is you start with an idea, you convert it to one of the patterns we support, which takes 5 minutes. Once you have a pattern, you should be able to prototype it. Again, 5 minutes. No qualifications. at the end of this prototype, you have something that is fault tolerant. There's no way you can hang it. And once you have your prototype, you can iterate over it, knowing full well no matter what you do, you will not be able to hang it. And then finally you deploy it. And you do this in the context of list of tasks, DAG, OpenMPI, graphs, data, doesn't matter, should not matter. Okay, so going back to our problem statement. As I mentioned, we are not going to talk about the other 10 primitives, we're going to talk about the new set. So let's start with this OpenMPI. What's the problem here? Well, this is the way typically an OpenMPI application is launched. You have hello world, it's been launched via MPI run. Fair enough? Right? What's the problem here? This hello world is not fault tolerant. It has no notion of timeout. And it has no ability to detect deadlocks. So the result is it's very, very frustrating to prototype. And those of us who have programmed know what I'm talking about. Right? You just want to try out a simple idea, and before you know it, you're getting sucked into the low-level details. So what's the problem statement? We want prototyping to be frictionless. In other words, I want to be able to launch any version of Hello World. It is a buggy one. In the serial world, for example, if you have a buggy serial piece of code, can you launch it? Yes. Do you get something meaningful out of it? 3 out of 10 times? Yes. The other 7 times, it crashes, but you're not paying a penalty. But in an OpenMPI application, when it hangs, guess what happens? System is frozen. Run this OpenMPI application on AWS, the public clouds. They charge you per minute, per hour. When it hangs, what happens? You are being charged for doing nothing. So we want to be able to launch any one of these versions, and it should always come back with a reply. There's a deadlock, there's a report. There's a timeout, there's a report. There's a crash, there's a report. And by the way, we're going to use the original code. We're not going to change anything. And we are going to use the original binary. We're not going to recompile things. Which means that if we're not going to change the hello world, we have to inherit these 3 properties, right? And going back to our statement, if hello world is not changing, the only parameter in play is MPI run. So we're going to replace it with SPM.Python, blah, blah, blah. So you end up with a statement like this. Now, that's a very unusual statement, because what I'm saying is for hello world to become fault tolerant, I'm going to run 2 very different parallel applications at the same time using the same resources. When was the last time that happened? Usually a set of machines are utilized by only one application. Here I'm going out of my way to launch 2 parallel applications. Because if hello world is not going to be able to detect the fact that it's stuck in a deadlock, it's outsourcing that to the second parallel application. And yes, that second thing is a parallel application, it's not a hack. Right? If I do this right, I have not only a drop-in replacement, because remember, this has to be easy to use, but I can now run multiple sessions of MPI run within a single session of SPM.Python. As I mentioned with respect to self-contained environments, once you acquire your 40 machines and it took 2 hours to get hold of that last machine, and within 5 minutes, if it crashed, and you still have 40 other experiments to run, you should not have to wait for another 2 hours. So here you are allowed to run multiple sessions one after the other. You end up with a flow that is like this. You can do checkpointing with like 2 lines of Python code. What if analysis like 1 for loop. Now, of course, for checkpointing, you have to do things on your OpenMPI application, but the logistics of how to pull it off is it's trivial. So going back to the statement, what is going on under the hood? It's a fairly delicate dance. Those of us who know the internals of MPI run, quite a few of these things are in common, but still SPM.Python has to do quite a few things. And then at the last stage, at the end of stage 5, OpenMPI application is launched, right? And then the first thing the application does is that it contacts the mothership, in this case it's SPM.Python. But I said we are using the original application. How is it going about doing something that there's no code for? So we have to play some tricks. Because remember, we are going to run OpenMPI application at speed. We are not going to slow it down, right? So if it's optimized, it can work at full capacity, If it's debuggable, it will be slowed down by whatever the compiler produces. We are not going to interrupt it. We want it to work at speed. These things, they take time. They are parallel systems. Just to detect deadlocks, we don't want to slow it down. We want to detect deadlocks in the real situation. So what are we trying to do here with this thing? What is the second parallel capability doing here in order to make this whole thing work? Well, there are two things. Think of it this way. The second parallel application is that, in effect, establishing a nervous system over our hello world. Okay? And the second thing is that the application is producing series of time series data, and it pushes all that data up into the nervous system. And it's the processing of this time series data, the side effects of it, that result in our application inheriting these three properties. So examples of time series data. I'm about to call this call, and it has these arguments. Oh, by the way, that call has finished. I'm about to call another call, and it has these arguments. All this has been pushed up into the nervous system. And in the background, the second parallel capability is kind of monitoring what is going on. And that's how you inherit these three properties, right? Now, if you look at the breakdown, there are three things that needed to be solved. I'm going to focus on the actual code. Remember, the goal here is, as I mentioned with the supposition, we want the developer to be able to express this thing with as little code as possible. So notwithstanding the fact that it's something very, very tricky on the back end, we don't want the developer to worry about these things. And of course, it has to be extremely efficient. So given that this is Python, you can do it in 60 lines. How does it look like? Well, in SPM.Python, everything is, like I said, a primitive, a parallel primitive. So the first thing you have to do is declare and create an instance of it. But I mentioned that SPM already has 10 other forms of parallelism. We are not interested in those 10. We want this one. That's one statement. That's a parallel closure. The next thing we are going to do is we're going to populate it. Those are 3 lines. And then after that, we're going to invoke it, which is the last line, the statement before return. That's it. It's not going to conclude until our MPI application finishes. And the status reports are invoked by this routine, and you simply dump it onto the screen. This is the sum total of what the developer has to write. Actually, because of the way the demo is written, you don't even have to write it this way. You can literally use what we provide. So what is the goal here? Again, remember, the supposition was whatever primitives we provide, they have to provide performance, but their API has to be close to where the developer is. And that is the reason why this thing is so small, notwithstanding some very tricky stuff happening in the background. So concluding here, this is what a session looks like. You have acquired resources saying import pool, and it doesn't matter where the resources are coming from. They could be from a local machine, LSF, Intel Grid, SunGrid, AWS. It does not matter, it should not matter. Then we import the demo code, the one that I just reviewed, and we invoke it twice, one after the other. We're using the same resources twice in the same session. So when, say for example, demo main crashed, the first one, the hello world crashed under the hood, those resources are going to be reacquired and made available to you. So by the time you invoke the second demo main, everything's still there. Because again, remember, Python guys are not going to put up with funky behavior. So this is basically as clean as it gets, right? So that's what the set of primitives allow people to do, to launch any OpenMPI application, and you end up having all these reports showing up on your desk. Notice in this one session, I'm basically using the same resources twice. I could introduce some other form of parallel capability in between the 2 demo mains, and it makes no difference, right? So talking about the second kind of parallel primitives for graphs and data. I'm calling these things hybrid flow because they're a combination of control flows and data flows. How many of us know what data flows are? Of course. Good. Everything else is a control flow. So this is a template. Can you read this? Good. I have a piece of work. I'm going to evaluate it. It's a Python statement. It doesn't matter under the hood how that piece of work is implemented. It could be written in Python. It could be written in C++, imported via the shared library API. It could be a co-process, or it could involve the GPU. It does not matter, should not matter, right? At the top level, this is what I'm doing. Now, if I'm a resource, I need to somehow acquire this work. So I'm going to write this piece of code. I have a for loop. The generator makes the work available to me. I'm going to evaluate it. Once in a while, I'm going to push out new work. Now, what I've just described here is the data flow. Work is made available to me. I simulate it. I do whatever I want with it. I generate a new piece of work, and it goes downstream. This is a classic data flow. What is the problem here? There's no control flow here. There's no system-wide control flow here. What that means is, imagine a situation where, how many of us have heard of, seen herds of animals running in the national park? Now imagine they were running in a straight line no matter what. There is no way that group of animals will survive the next generation. They will all be cleared. What we need is a way for the herd of animals to navigate. What we need is for this data flow to navigate the parallel landscape. And we need for that control flows. We need a way to interrupt this herd of animals, or this herd of compute resources. That's what this looks like. This is literally the code. This is a parallel exception. How many of us know what a serial exception is? Serial exception? No? Exception is a way by which to interrupt the normal flow of execution. This is a parallel version. So what this says is, one of the resources in our herd of compute resources finds out something interesting, and it throws this exception. That's that one line of code. Everybody else is interrupted in response to that. This is a game changer. That's why I'm calling these things hybrid flows. And we'll see applications shortly. And just for good measure, we're going to introduce parallel data structures, synchronous and asynchronous. Right? You end up with a piece of code like this. Now, I mentioned that you can use this to solve problems in data, as well as you can use this piece of code for data analytics as well as graph analytics. Everything that I described, I did not qualify any of my statements, which means that you can use this piece of code for both of those situations. Right? How's that possible? It gets even more interesting. The same piece of code can be used to express 8 different forms of parallelism. They are not just different, they are distinct. So any one of these 8 cannot be implemented using the other 7. But it's the same piece of code as far as the developer is concerned. How is that possible? Guesses. How can I describe 8 different forms of parallelism with the same code? I'm going to change the semantics of the stuff in maroon. Remember, if you go to the previous code, all the stuff in, I guess, purple are special parallel primitives. I'm going to change the semantics of that. That's it. I have one set of semantics. I have this form of parallelism. This is used when doing machine learning, where the green code here is communicating, the generator is making work available, and then when I push out work, it goes to any one of my neighbors depending on a graph. So from a system point of view, this is what it looks like. This is used in machine learning. I change the semantics one more time. It's the same green code, by the way. I change the semantics one more time, and I'm able to do speculative work now. All the generators are making the same work available to all the resources. And then one of them decides that, oh, it found something interesting, it throws an exception, it stops everybody else from proceeding. And I now have speculative work. I can leverage this in AI, machine learning, genetic algorithms, doing speculative work, all kinds of things. But it's a fundamentally different form of parallelism. The graph is completely different. You can just see it visually. I change the semantics one more time, and I have BASP. This is a way to process graphs. The generator is making work available that was generated in the previous iteration, and the emitter is making work available in the next iteration. This is what Google uses for Prangle, for graphs. Change it one more time, I have the classic data flow. Folks, the only thing that has changed are the semantics. Right? And on it goes. So that's what these primitives allow people to do. And of course, this is in the context of Python. So we end where we began, which is a review of two sets of primitives. They are, again, like I said, with the supposition, they have to be close to where the developer's intent is and not close to the hardware, but that should not be used as an excuse to say we don't deliver on performance. This is incredibly fast, 50,000+ messages per second kind of numbers, right? Now, OpenMPI is in limited beta right now. It's a self-funded company, so have to be careful. No spare dime or anything like that. And the hybrid flow, it's going to be available on January 4th. If any one of you is interested in any of these things, do get in touch with me. You'll be pleasantly surprised, right? The days of, all of us have heard of Hadoop, right? And what is the buzz around it? It's going to solve all our data problems. It's going to solve all our graph problems. We know in our bones that is a bunch of blah, blah, blah. This is truly exciting stuff. So, looking forward to engaging with any one of you. With that, I yield.